Today's lesson is over antiderivatives, or more specifically, antiderivative is called an integral, integral. So I wanted to start today by going over what an integral looks like, and then we'll look at some examples from both lesson 23 and 24. Here is the way that you write an antiderivative formally. This is the integral sign. This whole thing is an integral. And the function f of x is called the integrand. Dx is your variable of integration. And if you have some values to plug in, a is known as your lower limit of integration, and b is known as the upper limit of integration. In other words, these are the boundaries, how far you're evaluating your original function, or your interval where the function starts and where it ends in the evaluation. And you read this as the integral from a to b of f of x d of x. And if you're plugging in limits of integration, then this is known as a definite integral. If you are not plugging in limits of integration, that type of integral is indefinite. Now, we are still going to use the power rule in reverse, like we did finding various antiderivatives. A few rules to keep in mind. If you have a definite integral and you're plugging in limits of integration, the lower limit of integration should be the smaller value. Excuse me. So if your limits of integration are turned around, then you have to write them in the proper order, and it will be the negative of what you're given. If your lower and upper limit of integration are the same, then the value of your integral is automatically 0. With a definite integral, let me show you the main theorem that we will use to evaluate definite integrals. And that rule is the Fundamental Theorem of Calculus, Part 2. Right here, and I'm just reading this straight from the page, if f is continuous over a closed interval AB, and capital F is any antiderivative of lowercase f over the interval, then the integral from a to b of f of x dx pardon me, is equal to capital F of b minus capital F of a. In other words, when you take the antiderivative and get that, you're going to take your upper limit of integration and plug that value into your integral or antiderivative first. The minus sign is required in your substitutions. And then the second go around, you'll plug in the lower limit of integration into your integral or antiderivative. So let's look at some examples. I'm going to start with some examples that are indefinite integrals. So first question, we have the integral of 7x to the 5th power dx. Now we're going to still, even though this is written differently, we're still taking the antiderivative by reversing the power rule. By the way, if you have any constants in an integral problem, move those constants to the front. Now, reversing the power rule, instead of subtracting 1 from the original exponent, if you were taking the derivative, you would actually add 1 to your original exponent. And instead of multiplying, you would divide your antiderivative by your new exponent. So this will become now x to the 6th power all over 6. And when I join the 7 with it, that gives us 7x to the 6th power over 6. One thing to remember, if you are solving an indefinite integral, then you need to put a plus c to represent any constant. If you have a definite integral, then the plus c is not required. Let's look at another example in which we are finding the antiderivative or the integral. Next problem, we have the integral from, just the integral of 1 over x to the 11th power dx. Before we can take the antiderivative or undo the power rule, we need to rewrite our positive exponent into a negative exponent. So that would become now x to the negative 11th power dx. Now, reversing the power rule, we will add 1 to our original exponent. And instead of multiplying, remember the opposite of multiplication is division. So we'll divide our antiderivative by our new exponent. And that gives us now x to the negative 10th power over negative 10. The last step, rewrite your negative exponent into a positive one. So the x to the negative 10th power will go back down to the denominator. So our final answer is negative 1 over 10 x to the 10th power plus c. Let's look at some examples, or let's look at some definite integrals in which we have to plug in values. And just a second, let me copy and paste our problems. Okay, evaluate the following integral. Before we integrate or even evaluate, we can distribute that 3x times x minus 5. So we'll rewrite this now as going from 0 to 2 of 3x squared minus 15x dx. Now we can integrate each term by reversing the power rule. For 3x squared, add 1 to the original exponent and divide your antiderivative by your new exponent. That will be 3x cubed all over 3, or just x cubed after the 3's cancel. Now the negative 15x, it's understood to be negative 15x to the first power. And again, by undoing the power rule, you add 1 to the original exponent, and you divide your antiderivative by the new exponent. And that will become negative 15x squared all over 2. Now we're ready to plug in our limits of integration. According to our Fundamental Theorem of Calculus, Part 2, we plug in our upper limit of integration first. So everywhere you see an x, plug in 2 first of all. So we now have 2 cubed minus 15 times 2 squared all over 2. The theorem contains a mandatory minus sign between your substitutions. And the second go around, we'll plug in the lower limit of integration, or 0, everywhere we see an x. And actually, that entire second part goes to 0. Back to the first substitution. 2 cubed is 8 minus 2 squared is positive 4 times negative 15 is negative 60 divided by 2. That will give us negative 30. Final answer is negative 22. Again, when you're using the Fundamental Theorem of Calculus, Part 2, you must have a minus sign in between your substitutions. Let's look at another definite integral that we need to evaluate. We have, and I'm making this one up, the integral from 2 to 3 of 2x dx. The first step here, use the power rule in reverse for antiderivatives. We have 2x to the first power. You add 1 to the original exponent, and you divide your integral by the new exponent. That gives us 2x squared over 2, which simplifies to x squared once the 2's cancel. Now we're ready to plug in our limits of integration. And according to your Fundamental Theorem of Calculus Part 2, you plug in your upper limit of integration first. So where we see an x, we'll plug in 3, minus in between your substitutions, and the second time around, plug in 2 for x. So our final answer is positive 5. Let's look at another definite integral, but for this definite integral, we have to plug in negative limits of integration. So let me screenshot this example, and we'll work it out. Let me make this a little bigger. Hold on just a minute. Now, the only thing we've learned so far as integrating technique is undoing the power rule. We need to, first of all, simplify this fraction before we can integrate. Well, since our entire fraction has a common denominator of y to the 6th power, then we can split this into 2 separate fractions. So y to the 8th over y to the 6th minus 2y squared over y to the 6th. And using the quotient rule for exponents, you're subtracting the exponents. We get now y squared minus 2 minus 6 is negative 4. Now we can use our power rule in reverse to find each integral or antiderivative. First term, I'll add 1 to the original exponent, and then divide by the new exponent, 2 plus 1. So that gives us y cubed over 3. The second term, you still add 1 to the original exponent, and you still divide your term or integral now by the new exponent. So that would be negative 2y to the negative 3 power, all over negative 3. The two negatives change to one single positive sign. And also what happens, the y to the negative 3 goes to the denominator, becomes a positive y cubed. Now we are ready to plug in our limits of integration. And you always plug in your upper limit of integration first. So we'll plug in -1 first everywhere we see a y. And because we're plugging a negative into our y's, I'm using parentheses. Mandatory minus sign in between your substitutions. The second go around, everywhere we see a y, we'll plug in -2. And at this point, it just becomes basic arithmetic. In the first pair of brackets, -1 cubed is -1. So we have -1/3. Right here, this will also become -1. So +3 times -1 gives us -3. So that becomes -2/3. Second substitution, -2 cubed is -8. So that gives us -8/3 for the first fraction. And this is -8 also. 3 times -8 is -24. And when we reduce that fraction, we get -1/12. Now, a few things we can do. Distribute that middle negative sign times everything in the second brackets. So we now have -1/3 minus 2/3 plus 8/3 plus 1/12. Now we can combine all the thirds because they all have the same common denominator. So that would give us, when we combine the numerators, +5/3 plus 1/12. We need to get a common denominator, which is 12, by the way. In other words, we need to rewrite 5/3 as something over 12. So 5/3 can be renamed as 20/12. Plus 1/12 gives us 21/12. The only thing I ask you to do with fraction answers is reduce them to lowest terms. So we'll divide both numbers by 3 to get our answer 7/4. I want to go over the basic trigonometric integrals that you need to know. And I'm going to pull them up from a website. Let's see. And I just searched on Google basic trig integrals. And let me find a better copy. Hold on just a minute. Okay, here are the basic ones that you need to know. On the second column, the integral of cosine is sine x. The integral of sine x is negative cosine x. The integral of sine squared x is tangent x plus c. I forgot to mention that. If you're plugging in limits of integration, then you don't need the c. Next, the integral of secant tangent is secant x plus c. The integral of cosecant x cotangent x is negative cosecant x plus c. And the last basic trig integral, cosecant squared x dx is negative cotangent x plus c. Let's go over a basic trig integral. Let me pull my whiteboard back up here. And let's integrate going from 0 to pi over 2, the integral of cosine x dx. Well, we just saw that the integral of cosine x dx is sine x plus c. We don't need the plus c because we're plugging in some values. Using the Fundamental Theorem of Calculus, Part 2, we'll plug in the upper limit of integration first. So that would be the pi over 2. A minus sign in between your substitutions. And the second go around, we'll plug in 0 for x. We know sine of 0 is 0. Sine of pi over 2 is sine of 90 degrees, and that's positive 1. So make sure for future lessons, might not necessarily be this particular lesson, that you know the basic trig integrals I showed you. This concludes today's lecture, and this was over again, just to recap, indefinite and definite integrals. Indefinite and definite integrals, all we used was the power rule in reverse, like we did finding antiderivatives. And if you have a definite integral, that means you have to use the Fundamental Theorem of Calculus, Part 2, to plug in your limits of integration and evaluate the entire integral.